Hi everybody. Here's a brief video tutorial about how I graded the exam and also some hints towards the answers. I'm not actually giving the answers on this video because there were several different versions of the exam, but I will get you through the first bunch of steps and take you up to just where the algebra begins. And then you can look at the problem and assign the values that were given in the problem. So something to note before we go any further is that where it says page 1 is probably not page 1 of your exam. This is the pulley problem, the one with the two pulleys. And page 2 refers to the projectile motion problem where the clown is being fired out of the cannon. And number 3 is the inclined plane. And problem 4, page 4, refers to the problem where there was a force given as a function of time, and also the car crash. And then page 5 was the bucket of water being swung over your head. And how I graded it. Here are the four problems that counted for the majority of your grade. The way I graded these was each one was out of 10, so for a total of 40 points. And so I took the total and divided it by 40 and multiplied it by 100%. And then I just took whatever these points were that you got. Most people got maybe 2 or 3 points or something like that, so I just tacked those right onto here. So the most anybody could get was 110, and a few of you did. So here's the problem that has to do with the cinder block, which is attached to the end of a thin light cord, and it has an upward force applied to the end of the cord. And that F of t indicates that this force is a function of time. So if there's your cinder block, here is F of t. Force is a function of time. And you still have, of course, the weight. A lot of people forgot that, and I was actually very merciful on that, because the important part of this problem was to take this function right here, and from that find the acceleration. When you are given the position as a function of time, the first derivative is the velocity. So the first derivative would be the velocity. That's equal to 2.8 plus 3 times 0.61 times t squared. The acceleration is the second derivative. That's going to be 6 times 0.61 times t. So the acceleration is not constant, and it was not appropriate to use the equations for constant acceleration, like the x equals x naught plus v naught xt plus 1/2 axt squared. Those are not appropriate equations to use here because a is not constant. It is a function of time. So once you have that, what I wanted for you to do was to take your free body diagram with f of t pointing upwards and mg points down, and the sum of these forces, just like always, equals the mass times the acceleration. Those are your two vectors. What that means is that if ft points up, it gets a plus sign, mg points down, it gets a minus sign, and that equals ma, where a is what you just found, 6 times 0.61 times t. 0.61 times t. So you plug that in here. You solve for a at whatever time is given. Plug that in here. Oops. And then you solve out the rest of the problem. And you solve for f of t. A lot of people just said, took the a and multiplied it by m, and they found ma. But actually f of t is equal to ma plus mg. So if you just forgot to add the weight on there, I was pretty merciful. I didn't take any points off for that at all. In fact, the main place you get the points were to take the derivative twice of this to get the acceleration. Okay, as far as the driver sending the text message and crashing a sports car, what I was looking for here is appropriate use of the words force, velocity, acceleration. If you use the word force as though it were some kind of quantity that somebody has, I wasn't very merciful in giving many points for partial credit. If you use the word force, it should have been in a sentence like this. The force that the car exerts on the SUV is equal and opposite to the force that the SUV exerts on the car. Newton's third law. That's very nice, and I would give a couple of points for that, but that means that if the SUV is big, that means it has a smaller acceleration, and the car, which is small mass, has a big acceleration, which is very bad news for the driver. However, what's happening here is that the airbags and also the crumple zones of the car are going to increase the distance and the time over which that acceleration needs to take place. And so even if you don't know how airbags work, any kind of indication that those things minimize your acceleration of the driver is going to be what's important for this problem. And acceleration is the change in velocity over the change in time. The bigger the time, the bigger the distance over which the acceleration takes place, over which the force is applied, the better the outcome for the driver of the car. And I think there was a homework problem about this as well. Okay, next page. Here we've got two masses that are connected by a thin light string over a massless frictionless pulley, and it's released from rest, and obviously the big one, the massive one, is going to pull the other one up. So in all cases, here's what I was looking for. It doesn't say anything about forces, but this is absolutely a question that involves forces. Here, let's just call these mass 1 and mass 2. So for mass 1, we have an upward force due to the tension and a downward force due to its weight, m1g. Same thing for box 2. This is number 2. Same tension pulling up. The tension is the same throughout the string when we're dealing with these idealized thin strings and massless frictionless pulleys. Here we've got m2g. Now, T does not just equal mg. The sum of these forces don't just kind of magically equal mg. Here's the way these free body diagrams work. T minus m1g is equal to m1a1, meaning the ones referring to this box. Mass 1 has acceleration a1. The total forces acting on mass 1 equals the mass 1 times its acceleration. Same thing for mass 2. T equal or minus m2g equals m2a2. These equations come from your free body diagrams, which are a step in the direction of actually writing some equations that we could actually write down. The last thing to realize about this is that one's going up and one's going down. They're both speeding up, so their accelerations have to be equal in magnitude. If that was not true, the string would be stretching out or snapping or something, and that's not what this problem is about. So the accelerations are equal in magnitude but opposite in direction. Now you've got a bunch of equations relating things that are known and things that are unknown. We don't know the values of the acceleration. You might not know both of the masses, but what you are given is some information about the distance that it fell and also how much time it took. What you have to do with this information up here is to use your equations of constant acceleration. And for this particular problem where it tells you how many meters and how many seconds, I saw an awful lot of people just kind of, ooh, there's meters and seconds, so I'm going to turn that into a velocity, and that was absolutely wrong to do, and I was pretty merciless about that. You could get, if you drew good free body diagrams, if you indicated that the sum of the forces acting on box 1 equals m1 times a1, if you wrote out how Newton's laws apply here, these are the ones acting on 1, and then if you wrote something like this. And I was picky about the vectors too. A lot of times people just kind of wrote F equals ma, sort of sloppy, without the vector signs. These are all the forces acting on box 2. And if you were kind of not using vector signs, I was not very merciful about assigning partial credit. Not using vector signs where they should be is the mathematical equivalent of bad grammar, and you need to learn how to use good grammar. Also, one of the things that I notice is that when people kind of use vector signs in some places and don't in other places, they very rarely get a right answer, which tells me that it's not just their physics grammar that's lacking, it's the physics understanding. So anyway, so the last step here would be to write, to use one of the equations for constant acceleration and relate the values that you are given here. Okay, so one of those 4 equations here, I'll just scroll back. one of these four equations. Okay, and that way you have those three pieces of information, one from each free body diagram. A1 equals negative A2, and then the last one is one of these equations here. So you have four independent pieces of information, and it's just algebra from there.